So now we'll talk about the role of salinity in determining the density of the ocean. So salinity plays a fairly complex and complicated role, but mostly the two main factors that determine salinity are, on the one hand, precipitation and evaporation, and on the other hand, influx of fresh water, either from rivers or melting ice, and that can be either sea ice or land ice, i.e. glaciers and ice shelves. And we'll talk about the role of ice in more depth in the next couple of lectures. So either influx of fresh water or also brine rejection, which happens when ice grows. But before we delve into a little more detail regarding these factors, let's talk a bit more about what is salinity really. So the ocean is full of salts, which makes it rather different than lakes and other freshwater bodies. And the composition of this is predominantly sodium chloride. So we have chloride makes up about 55% of all the salts, sodium around 30%, and then there's a whole range of other minor constituents: sulfate, magnesium around 4%, and then we have calcium, potassium at around 1%. And so throughout the ocean, these percentages are fairly constant, which means the salts in the ocean are pretty well mixed. Next, for most of the ocean, the range of salinity is fairly narrow. It ranges from about 34.6 to 34.8 parts per thousand. So for 1,000 parts of water, there's about 35 parts of salt. And so this range is only 200 parts per million. And parts per thousand is often abbreviated as PPT. But especially the surface deviates from this quite substantially sometimes, especially when you have things like influx of fresh water or a lot of evaporation or a lot of rainfall or snowfall. Then you can get quite a bit more or less than the 35. And so a typical salinity profile, I'll draw a couple here, analogous to the profile for temperature I drew in the last video. We have now salinity in parts per thousand on the horizontal, and on the vertical axis we'll have depth again in meters. And again, we will have this shallow surface mixed layer here, surface mixed layer, SML. Not only the temperature is pretty well mixed, but also the salinity. And then you will have a range of depths below that where you have steep changes in salinity, and that is called the halocline. The halocline derives its name from halo, Greek for salts, and the cline means a layer of rapid change. So in regions where you have a lot of evaporation, especially in the tropics and subtropics, you will have really high salinity because only the fresh water evaporates and leaves behind a very salty top layer, and then that decreases quickly to about 35, and the depth of the ocean has a fairly uniform salinity profile. And so this is typical for low latitudes, broadly speaking. There are regions, especially in the intertropical convergence zone, just south of the equator, where you have a lot of precipitation, and then the profile looks a lot more like this. Now, in high latitudes, you have sometimes the opposite effect, where you have a lot of precipitation and it's much cooler, so you don't evaporate as much. You have this inverted profile where you have low salinity and then it increases in the halocline and then converges to the same salinities at depth. So this is mostly a story now of precipitation and evaporation. Sometimes you call that, the difference between them, you call this E, evaporation, minus precipitation. So you would have a high surface salinity when you have high E minus P, and a low surface salinity when you have low E minus P. What I haven't considered in these profiles is the role of influx of fresh water or brine rejection. And we'll talk about that next.